Let's talk about a few important points regarding hypothesis testing. First, let's talk about the hypotheses. Remember that the first step in a hypothesis test is to come up with the null and the alternative hypotheses, right? And in doing so, hopefully you are able to identify the parameter of interest. In the examples we've done so far, we have been looking at the population mean mu, but in principle, right, you can test on other population parameters as well. So, for example, the population proportion, and so on and so forth. So that leads me to the first point that I want to make, which is that we always conduct tests on population parameters, okay, not sample statistics. Now, if you think about this statement, it makes perfect sense, right? Because given the sample, you know what the sample statistics are. You know their values. For example, you know the sample mean, right? So if somebody makes a statement about the sample mean, you can tell whether that statement is correct or not. But if somebody makes a statement about the population mean, you don't have access to the population, and so you don't know what the population mean is. And so to analyze whether that statement is valid, you have to do a hypothesis test, and when you test on the population mean, not the sample mean. Right? Yeah. The second point I want to make is that the hypothesized value mu sub 0 is the same in both the null and the alternative hypotheses. So let's look at an example. Recall we did an example where a professor claims that it takes less than 170 minutes on average to finish a test, right? In that example, the statement that goes in the null was the population mean is less than or equal to 170, and the statement that goes into the alternative hypothesis is that the population mean is greater than 170. Okay. First off, notice the notation here, right? Is mu, so we're testing on the population parameter. In this case, the population mean, and then the hypothesized value is 170, right? Which is the same in both the null and the alternative. Okay. Now the second point I want to make is about the level of significance. Remember that we can test at any level of significance, right? Although we pay attention to the 1%, the 5%, and the 10% levels of significance. Now, the level of significance plays an important role in deciding whether the null can be rejected, right? Okay, why is this? Because if you recall, we use the level of significance alpha to find the critical values if you use a critical value approach, right? Because it determines the critical values, and we compare the p-value against it, right? If you use a p-value approach. Okay, because of the importance of the level of significance, what we want to do is that we must choose a level of significance alpha before a hypothesis test is conducted. Okay, you cannot calculate the test statistic, find the p-value, and then go back and choose the level of significance, right? Doing that is like knowing the result of a game and then trying to go back in time to bet on that game, right? You cannot have the cake and eat it too, if you will. Okay. The next thing I want to talk about is the sampling distribution of the of sample statistics. Okay. Now remember that in the examples that we've done so far, we have been using the z-table to find the critical values and the p-values, right? As you will see later on, when we don't know the population standard deviation, we're going to use the t-table. Okay? Now, in order to use the z and t tables, we need sample statistics to be normally distributed. Okay. Now, when it comes to the mean, which is what we've been looking at, sample means are normal, right? If either the underlying variable is normally distributed, okay, or if the sample size is sufficiently large. Okay? And by sufficiently large, we're talking about sample sizes of greater than or equal to 30 observations, right? So that we can apply the central limit theorem. Remember that the central limit theorem states that regardless of the distribution of the underlying variable, as long as you have a large enough sample size, the sampling distribution of the sample means will be normal. Okay? And so if we have, the idea is if the sample size is small, what we need to assume is that we need to assume that the underlying variable is normally distributed. Okay. Again, the idea is that we want to be able to use the z or the t table to find critical values and p-values. Okay. Now the last thing I want to talk about is what's called the rejection region. Let's first look at upper tail tests. Now for upper tail test, remember that we reject the null if the test statistic is greater than the critical value, right? And the critical value for an upper tail test is z sub alpha. Okay. So if you draw the number line, and if this is your z sub alpha, then as long as the test statistic is above z sub alpha, you're going to be rejecting the null, right? Now the interval from z sub alpha to, in this case, positive infinity is what we call the rejection region of upper tail tests. Okay. For lower tail tests, the decision rule is we reject the null if the test statistic is less than negative z sub alpha. Right? Again, if you draw the number line and then negative z sub alpha is right here, then the rejection region will be the region below negative z sub alpha. Okay. And then for two-tail tests, right, the idea is we reject the null if the test statistic is less than negative z sub alpha over 2, right? Or if the test statistic is greater than z sub alpha over 2. Okay. And so if you draw the number line for this situation, you put negative z sub alpha over 2 and then z sub alpha over 2. Then we have two rejection regions, right? The first one is a region above z sub alpha over 2. And the second rejection region is the region below negative z sub alpha over 2. Okay. Okay. So I hope this makes sense.